Good morning, students. So in the previous class we have discussed about the various Boolean algebra functions and laws of Boolean algebra. Continuing with that one, the next law is complementarity law, where a variable is considered with its complement. That is, if I am taking the variable x here and I am ORing the operation with x bar, complement of the x variable is x bar is equal to 1. In the same way, when we are doing an AND operation, x and x bar, that is, x is a variable and the complement of x is x bar, will yields us 0. So how we are going to get x plus x bar is equal to 1 and x into x bar is equal to 0. Proving it with the help of the logical gates, consider the one variable as x and another variable as, if I am giving the same to the NOT gate, it will become x bar. Both should be inputted to, because we are using a OR operation, we have to use a OR gate here. The first input will be x. When x is inputted, the same x is inputted to the NOT gate, it will become x bar. As we know, a OR gate is always having two inputs, that is x and x bar will be considered as the two inputs for OR gates. Here x is given as input to the NOT gate, which becomes x bar. One of the input of OR gate is x and another one is x bar. When we are ORing this operation x plus x bar, it becomes x plus x bar. So how x plus x bar is equal to 1 means, if I am considering x value as 0 and inputting it to the gate, this first input will be considered as 0. Because I am inputting the same 0 to the NOT gate, it will complement and it will become 1. When 0 and 1 is there, the output of OR gate is always 1. If you are considering the value of x as 1, if I am inputting x as 1, the first input will be taken as 1 and the second input, the 1 will be given to the NOT gate input and it is going to complement that input, that is 1 will become 0. Now the inputs are 1 and 0. When 1 and 0 are the inputs, the output of OR gate is 1. So hence it is proved that if the complement of x bar is used with OR gate, we are going to get the 1. In the same way, if you are using x dot x bar, that is ANDing the operation, AND operation has been used, x dot x bar is equal to 0. Same way, I am going to consider x as input and it will be given to the AND gate here. Here we are going to use the AND gate and the same input is given to the NOT gate and it becomes complement, that is x bar. Then it will be inputted to the AND gate. Then the output will be x dot x bar. If I am considering x is equal to 0, then the input of x is 0, the first input of AND gate is 0. If the same 0 is inputted to the NOT gate, it will complemented and it will become 1. As we know, 0 multiplied by anything will yields you 0 itself. In the same way, if I am taking the input of x as 1, the first input of AND gate is 1 and the same 1 is given to the NOT gate and the output of NOT gate will be 0. 0 into 1, once again we are going to get the 0. That's why we have written that x dot x bar is equal to 0. That's why we are saying that complementarity laws, if in any Boolean expression, if we come across with x plus x bar, directly we can replace it with 1. If you are coming across with x dot x bar, you can replace it with 0. Because if x is 0, x bar is 1. If x is 1, x bar is 0. Any one of the input may be 0. If you are multiplying this one, you are going to get the 0. In the first law, if the x value is 0, the complement of x bar is, x is, that is 1. 0 plus 1, you are going to get 1. If the value of x is 1, the complement of x bar is 0. If you are adding these two you are going to get the 1. If any one of the input is 1 in OR operation, you are going to get the 1 as output. If any one of the input is 0 in AND operation, you are always going to get the 0 as output. This is what complementarity law states. The next law is commutative law. In commutative law, we come across with two statements, that is one for OR and one for AND. The first law states that x plus y is equal to y plus x. Both are same. If you are changing the position of the variables either to the left hand side or right hand side to the plus sign, it won't make any difference. In the same way, in x dot y is equal to y dot x, if you are changing the position of the variables, it does not make any changes in the expression. That is what commutative law states, that if you are proving that one by making use of the logical gates. For this we are using an OR gate. We are taking x as a first input and y as a second input, and we are giving it to the OR gate. We are giving it to the OR gate, and the output of this gate will be x plus y. In the same manner, if I am interchanging the variables, the first input is y and the second input is x, then you are going to get the output as y plus x. If I am considering the truth table, for this, if I am considering the truth table, we are having two variables here, that is x and y. We are having the two variables, that is x and y, and we can able to make the combination up to maximum up to 4, that is if both the inputs are at 0 0, or if x is 0 or y is 1, if x is 1, y is 0, if x is 1, y is 1, then what will be the output of x plus y and y plus x? First we will consider for x plus y. 0 plus 0, 0 or 0 is equal to 0 itself. 0 plus 1 is equal to 1, 1 plus 0, 1. As we know, 1 plus 1 also yields you 1 itself. This is what the output of x plus y. If I am getting the first input as x and second input as y, I am going to get this output. Now, interchanging the variable. First I am going to consider y, then I am going to consider x. 0 plus 0, once again 0 will be the output. If the y is 1, x is 0, 1 plus 0, I am going to, if any one of the input is 1, the output is always 1. If y is 0, x is 1, then also I am going to get 1 itself. If y is 1, x is 1, then also I am going to get 1 itself. These two columns are identical. So, you can able to write, if the expression is given in the way that if it is x plus y, you can change it into y plus x. Both are identical. This is for OR operation. This is for OR operation. For AND operation, I am going to consider two AND gates. In the first AND gate, the first input will be the x and the second input will be the y, and the output is x dot y, x dot y. If I am considering the first input as y and the second input as x, the output of this one is y dot x. Okay. Once again, for the same, I am going to consider two inputs, that is x and y. In the first one, that is x dot y and y dot x, x dot y and y dot x. Now multiply by considering first input as x and second input as y. 0 into 0, I am going to get 0. 0 into 1, we are going to get 1. 1 into 0, we are going to get 1 as a, sorry. 0 into 1, we are going to get the output as 0. 1 into 0, we are going to get the output as 0. if both the inputs are high, then only the output is 1. If any one of the input is 0, the output is always 0. This is what AND operation suggests. Now, if I am considering the first input as y, second input as x, 0 into 0, 0, 1 into 0, 0, 0 into 1, 0, 1 into 1, 1. Hence, both the columns are identical. That is, x plus y x dot y or y dot x, both the columns are identical. So, you can able to write either x dot y or y dot x in any of the Boolean expression which we are going to consider in the future classes. Next, we are continuing with the associative law. Once again, we come across with two laws. These laws states that x plus y plus z is equal to x plus y of plus z. Associative law of addition, and the second law is x of yz is equal to xy of z. Associative law of multiplication. If I am considering, once again, if I am considering the gates to implement these two laws, the first input will be x and it will be taken to the OR gate, and the second input will be y for the second gate, and z will be treated as second input. These two will be added first by making use of a OR gate, and the output of this one will be y plus z. Once again, I am considering one more OR gate, and the first input for the OR gate is x, and the second input is the output of the first gate, that is y plus z. If I am inputting it to the OR gate, the output will be like this: x plus y plus z. X plus y plus z will be taken as a single term, and y plus z, x plus y plus z, where we are saying that it will be equal to the x plus y of plus z. For that, I am taking an OR gate here is equal to, I am going to taking a OR gate here, and the input for that OR gate is x and y, and the output of this gate will be x plus y. If I am inputting x and y to an OR gate, the output will be x plus y, and I am taking in one more input and a second gate, and I am considering it as a z. The output of the first gate will be taken as input for the second gate, and z will be considered as the second input. If I am considering this expression, x plus y will be treated as a single term, that is x plus y plus z. We are saying that both are equal or both are identical. If I am writing the expression x plus of, by opening a bracket, y plus z closing a bracket is equal to, first I am putting the brackets for x plus y, then plus z, both are identical. To prove that one, if I am considering the value of x is equal to 0, substitute the value of x to both the expression. First I am considering x plus yz. If x is treated as 0, plus yz is equal to 0 plus x is equal to, by the properties of zeros and ones, the first law, in Boolean algebra we have discussed that x plus 0 is equal to x, or 0 plus x is equal to x, it completely depends on the x value. In the same way, we are considering y plus z as a x here, 0 plus x, that is we are remaining with y plus z itself. In the same way, if I am substituting the same value here, that is x 0 plus y plus z. 0 plus y means y itself, y plus z. We are left with y plus z. Hence, LHS is equal to RHS. The first theorem will be, the first law will be proved. Hence, the first law will be proved. Now, we are getting into the associative law of multiplication. Associative law of multiplication. For multiplication, we need to use the AND gates. I am taking a first gate with input y and z first AND gate with the input y and z, and the output of this gate will be y into z, and I am taking a second AND gate, and the input for the second AND gate is x here, and the second input will be yz, and the final expression output is x into yz. Yz will be treated as a single variable, and the output will be x yz is equal to, we have to write the RHS side, right hand side, that is xy should be considered first. So the first input of the AND gate is x, and the second input is y, the output is x into y, that is I am writing directly it as xy, and the and the next input is z for the second gate. The first input is xy and the second input is z. If I am providing it for a AND gate, the output will be xy into z. Once again, we have to prove LHS is equal to RHS. Same way, if I am substituting the value of x as 0, 0 into yz. As the properties of zeros and ones, if 0 multiplied by anything, you are going to get 0 itself. For the second expression, that is RHS side, if I am substituting the value of x as 0 into y dot z. 0 multiplied by anything 0, 0 multiplied by 0 dot z, then once again 0 into z, I am going to get 0 itself. In both the cases we are going to get 0 itself. That is why we are writing it as a LHS is equal to RHS, hence proved. This is the law of associative law of addition and associative law of multiplication. And the next one is distributive law. Once again we come across with two laws here, for OR operation, for AND operation, for AND and OR operations. This one is for AND operation and this one is for OR operations. So first we are going to write the logic circuit for this left hand side, then for the right hand side. If I am considering x as input, if nothing is written, we have to consider it as there must be a dot and it is an AND operation. We need to multiply these two. So I am writing it as x as an input for an AND gate. Then I am going to consider an OR operation here because y plus z is there. I am going to consider an OR gate, and the first input for that OR gate is y and the second input is z. If both are inputted to a OR gate, the output of this gate is y plus z. Next, considering an AND gate, the first input will be x and the second input will be yz. If I am providing it for an AND gate, the output will be x of y plus z. That is, we are ANDing this operation. Yz is ANDed with x. That is, x is ANDed with yz. This will be the output. In the same way, if I am considering the right hand side, that is, x will be considered as the first input for an AND gate, y will be the second input for an AND gate. If I am providing both the input for an AND gate, we are going to get xy as output. In the same way, if I am considering x as an input for second AND gate and z as an input for second AND gate, the output will be x into z. If both these are inputted to a OR gate, if both these output of AND gates are inputted to a OR gate, we are going to get xy plus xz. Xy plus xz. We can prove it by making use of a truth table, whether left hand side is equivalent to right hand side. Consider, here we are having three inputs. Here we are having three inputs, x, y and z. If you are making a combination 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1 double 0 1 0 1 1 1 0 1 1 1. Total 8 combinations can be made here. For this we need to find out whether LHS is equal to RHS. Whether LHS is equal to RHS. First I am going to consider the left hand side, that is x dot y plus z. We need to find out, first we need to find out the y plus z, that is 0 plus 0 0, 0 plus 1 1, 1 plus 0 1, 1 plus 1 1, 0 plus 0 0, 0 plus 1 1, 1 plus 0 1, 1 plus 1 1. I have considered here only y and z columns, because we need to add y z columns first, then we have to multiply it with the x column. That's why we have added y z column first and put the result or output of that y plus z in this column. Now consider x dot y plus z. Now you have to consider this column and this column. Only you have to consider these two columns, and you have to perform the AND operation. You have to perform the AND operation. That is 0 into 0, you are going to get 0, 0 into 1, 0, 0 into 1, 0, 0 into 1, 0, 1 into 0, 0, 1 into 1, 1, 1 into 1, 1, 1 into 1, 1. This is the output of x dot y plus z. If the expression in the form of x dot y plus z, you are going to get this output. For writing the second expression, I am going to erase this one. Continuing with that is RHS. First we need to find out xy and xz. First we need to find out xy and xz. First I am multiplying xy column. Considering these two columns, I am multiplying the values. 0 into 0, 0, 0 into 0, 0, 0 into 1, 0, 0 into 1, 0, 1 into 0, 0, 1 into 0, 0, 1 into 1, 1, 1 into 1, 1. Now considering x and z columns, 0 into 0, 0, 0 into 1, 0, 0 into 0, 0, 0 into 1, 0, 1 into 0, 0, 1 into 1, 1, 1 into 0, 0, 1 into 1, 1. Now we are having xy and xz. Now we need to add these two values, that is xy and xz need to be odd. That is, we need to add the xy and xz. Now I am writing xy plus xz. These two will be considered. 0 plus 0, 0, 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 0 plus 1, 1, 1 plus 0, 1, 1 plus 1, 1. These two columns are identical, this one and this one. These two columns are identical. The first 5 outputs are 0. Here also the first 5 outputs are 0. The last 3 outputs are 1. Here also the last 3 outputs are 1. Hence this law proved. Hence the first, that is x dot y plus z is equal to xy plus xz. If the expression is given in this way, you can also write it as xy plus xz. If the expression given in this manner, you can able to replace it with x dot y plus z. Now we are considering the law, distributive law, the second distributive law, that is x plus yz is equal to x plus y and x plus z. For this I am going to write the logic circuit diagram. First we need to consider the input as x, which has to be the first input of an OR gate, the first input of an OR gate. Then we have to multiply y and z, that is it has to be ANDed. Y and z needs to be ANDed first, then it has to given to the OR gate. So I am considering the AND gate first input as y, the second input as z, and it will give you y into z. If the same thing is inputted here, it will give you x plus yz. Because we have used the OR gate, first input is x plus the second input is yz, both will be added. And the RHS will be like this. First we need to OR x, y, then xz, then we have to multiply both the expressions. The first input is x here, the second input is y here, and it has to be given as input for an OR gate. And the next one is x is input here, z is the second input, and it is given to the second OR gate input. And the output of the first OR gate is x plus y, and the output of second OR gate is x plus z. If both the outputs of OR gates are given as input for the AND gate, it will become x plus y into y plus x plus z, x plus z, x plus z. To prove this one, we are considering the RHS, that is x plus y into x plus z. We are simplifying this one, that is multiply x into x, normal simplification, then x into z plus xz, then y into x plus xy. You can able to write yx or xy, then y into z. As we know, x dot x always yields you x itself, irrespective of the value of x. If x value is 0, if you multiply 0 by 0, you are going to get 0. If the x value is 1, 1 into 1, 1. That is, xx is equal to x. By the law of x into x is equal to x, we can replace it with x, then xz plus xy and yz. Here, we can able to take the x common in these three, that is x will be taken common and the expression will be written as 1 plus z plus y plus yz. If you are adding any variable with 1, you are always going to get 1 itself, that is x plus 1 is always giving you 1 itself. X plus 1 is always giving you 1 itself. Then I can able to write it as x into 1 plus yz. X into 1, once again x into 1 properties of zeros and ones. X into 1, it completely depends on the value of x. If x is 0, the output is 0. If x is 1, output is 1, that is x. Then I can able to write it as x plus yz. This is how, that is what LHS, that is x plus yz. Hence, it has been proved, x plus yz. First we have considered the RHS side, that is x plus y of x plus z, and we have get the solution as x plus yz, which is LHS side. Both are equal. It is also proved with the help of a truth table. In the same way, we are having three variables, that is x, y and z. For that we have written the truth table here. First we need to find out the yz by considering these two columns. 0 into 0, 0, 0 into 1, 0, 1 into 0, 0, 1 into 1, 1, 0 into 0, 0, 0 into 1, 0, 1 into 0, 0, 1 into 1, 1. Now we have to add x column and yz column. 0 plus 0, 0, 0 plus 0, 0, 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1, 1 plus 0, 1, 1 plus 0, 1, 1 plus 1, 1. This is the LHS side. This is the LHS side. Now we have to consider the RHS side. First we need to add x and y, then x and z. X and y, 0 plus 0, 0, 0 plus 0, 0, 0 plus 1, 1, 0 plus 1, 1, 1 plus 0, 1, 1 plus 0, 1, 1 plus 1, 1, 1 plus 1, 1. Now we have to add x and z columns. 0 plus 0, 0, 0 plus 1, 1, 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1, sorry, once again, 0 plus 0, 0, 0 plus 0, 0 plus 1, 1, 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1, 1 plus 1, 1, 1 plus 0, 0, sorry, 1 plus 0, 1, 1 plus 1, 1. Now we have to multiply these two. 0 into 0, 0, 0 into 1, 0, 1 into 0, 0, 1 into 1, 1, 1, 1, 1 and 1. 1 into 1, 1, 1 into 1, 1, 1 into 1, 1, 1 into 1, 1, 1 into 1, 1. So this is the RHS side. Both the columns are identical. The first 3 outputs are 0 and the next 5 outputs are 1. Here also the first 3 outputs are 0 and the next 5 outputs are 1. Hence both the columns are identical. LHS side is equal to RHS, hence proved. And the next one is absorption law. As the name itself suggesting that it is going to absorb the left hand side, that is x plus xy is equal to x. It is going to absorb entire expression and it will yield you only a single variable. Here also it is going to absorb the entire expression and yields you a single variable. How we are going to get this thing? First we are going to write the logic circuit for this. First we have to consider xy as input for an AND gate. If I am giving x as first input for an AND gate, y as second input, it will give you x into y. If I am taking x as a input for a OR gate, first input for a OR gate, xy as a second input for a OR gate, I am going to get x plus xy, x plus xy. We have to prove that it is equal to x. It is equal to x. X plus xy always gives you x itself. That we have to prove. We are going to prove it by truth table as well as by simplifying the expression. Consider it in an expression. X plus xy, that is RHS side. Take x as common here. If I am taking x as a common here, then we will be left with 1 plus y. As the properties of zeros and ones, 1 plus y always gives you 1. Irrespective of the value of y, you are going to get 1 itself. That is, x plus 1 is equal to 1 itself. That is, we can able to write x into 1. As we know, x dot 1 is equal to, it is completely dependent on the x value, will gives you x itself. If the x value is 0, the output is 0. If the x value is 1, the output is 1. So we can able to write it as x into 1 is equal to x. Hence the RHS side, that is right hand side, hence proved. In the similar way, here also I am going to write the first, I am going to consider x and y as two inputs for a OR gate, and the output of this OR gate will be x plus y, and I am going to consider an AND gate, and the first input for that AND gate is x, and the second input will be x plus y, and it will gives you x into x plus y. We have to prove this one is also equal to x itself. Consider the expression, that is left hand side, x into x plus y equals to, simplify the expression, that is xx plus xy. As we know, xx can be replaced with x itself. x is equal to x itself. Now take the x as common. Now take x as common, we are left with 1 plus y. As we discussed here, the same operations has to be carried out, that is x into 1 which is equal to x, which is the RHS. X plus xy is also equal to x. It has been proved with the help of the simplification. Now we have to prove it with the help of a truth table. We are having only two inputs, that is x and y, 0 0, 0 1, 1 0, 1 1. Total 4 combinations can be made with the help of two variables. Now first we need to consider x we are already having, we have to find out xy, that is you have to multiply these two columns, 0 into 0, 0, 0 into 1, 0, 1 into 0, 0, 1 into 1, 1. Now LHS side, that is x plus xy, 0 plus 0, 0, 0 plus 0, 0, 1 plus 0, 1, 1 plus 1, 1. This is the RHS and this is the LHS. Both are identical. Hence proved. The first one has been proved. Now we have to consider this one. For that we have to add x plus y. We have to consider x plus y and we need to add those two columns. 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1, 1 plus 1, 1. Now we have to find out x of x plus y. We have to consider these two columns and we have to consider the values 0 into 0, 0, 0 into 1, 0, 1 into 1, 1, 1 into 1, 1. This is the LHS, sorry, this is the RHS and this is the LHS in this expression. 0 0 1 1, 0 0 1 1. Both are identical, hence it has been proved. Absorption law. If you are considering the expression x plus xy, directly you can replace it with x. If you are considering x of x plus y, it can be directly replaced with x. So that's it for today's class. Tomorrow we are going to discuss about some more Boolean algebra, laws of Boolean algebra, and we are going to recall all the Boolean laws that we have discussed so far. That will be helpful for your coming chapters, coming topics. To simplify the expressions, you have to remember all these things. Just go through all the laws what we have discussed until now, and I think we may be left with one more law. Then we are going to brush up with all these laws once again, and we are continuing with the De Morgan's theorem. Thank you.